In this series of videos, I'm going to go over the basics of pipelining, and I'll start with the really simple stuff, and I'll add some layers of complexity. So first up, let's start with the most obvious analogy for instruction execution with pipelines, and that would be a car manufacturing plant and an assembly line. Okay, let's start with an unoptimized plant where there's one car being produced at a time, right? And so all the workers are busy working on different aspects of the car all at the same time. And let's say it takes about 24 hours to build one car. So after this 24-hour window, you have one car that rolls out of this plant. And then everybody gets to work on building a second car, right? And then 24 hours later, this car rolls out and so on. So this is an unoptimized design because there's no parallelism. There's only one car being worked upon at a time, right? So in terms of parallelism, it's only one car at a time, and the resulting throughput rate is one car every 24 hours. Okay, so now let's move on to a more optimized design where I take that entire car building process that takes 24 hours and break it up into 3 equal size stages, each taking about 8 hours. And that's what I'm showing over here with stages A, B, and C. So in stage A, I perhaps work on the engine. In stage B, I work on the body or the chassis of the car. And in stage C, I perhaps work on the paint job, paint and testing and so on. Okay, so at first, there is a car and there's a specialized group of workers that works on the engine, right? And so they spend the first 8 hours doing all of their tasks and producing the engine for car number 1. After those 8 hours, this car now rolls into stage 2, where there's a different group of workers that specializes in building the body. And now the group of workers that work in stage A are free to start building a second car, right? So there's a second car that now starts getting built in stage A by the workers of stage A, right? So at this point of time, there are 2 cars that are being simultaneously produced. There's car number 1 that's having its body built, and car number 2 that's having its engine built. 8 hours later, this car now moves into stage C. The second car moves into stage B. And again, the workers in stage A are free to start working on a third car, right? And this is a steady state. So in subsequent time steps, you'll have a situation where there are always 3 cars in production at any given point of time. There'll be one group of workers that are working on the engine for a given car, a different group of workers building the body for a different car, and a different group of workers that are doing the paint job for a third car, right? So now your parallelism has increased. There are 3 cars that are being simultaneously produced, and if you look at the throughput rate, you have one car rolling out of the plant every 8 hours, right? There's one car rolling out here, a second car rolling out over here, a third car rolling out over here, right? So every time stage C finishes, there's a new car that is finished, and this gap, as I said, is only 8 hours, right? So our throughput rate and our parallelism has gone up by a factor of 3x. And that's why you do pipelining. You take one large monolithic task, break it up into 3 different subtasks, each being done by a different resource. And that's what increases the performance. Okay, so now let's go back from this car assembly analogy, car assembly line analogy, back to executing an instruction on a pipeline. Let's go over here to the unpipelined case. So if I'm trying to execute an instruction without any pipelining, there's a certain sequence of circuits that has to be executed. First thing I do is I fetch an instruction, then I decode that instruction, and then finally I execute that instruction. And only after I've finished one instruction in its entirety do I start to work on a second instruction, right? And so then I start doing fetch and decode and execute for instruction number 2. Right, so again, there's no parallelism over here. So now when I move down to this design, I break it up into 3 stages, where the first stage is a circuit that does fetch. The second stage is a different circuit that does decode. and C is a third circuit that does the execute. So, instruction number 1 is fetched in cycle number 1, right? So this is time unit number 1, which I'm calling a cycle number 1. At the end of cycle number 1, the instruction has been fetched. It now moves to a different circuit, which is now going to do decode. So instruction 1 is now in the decode stage. And this frees up the fetch unit to start bringing in instruction number 2. Okay, and then I move to cycle number 3, where instruction 1 can now move on to the circuit that does execute. Instruction number 2 can move on to the circuit that does decode. And since the fetch stage is now free, it starts to fetch instruction number 3. And this is a steady state. 3 instructions being worked upon at the same time. Instruction 1 is being executed. Instruction 2 is coming behind it, where it is now being decoded. And instruction 3 is coming even further behind it, where it is being fetched. Okay, and so, at the end of cycle 3, one instruction has finished in its entirety. It now graduates and leaves the processor. Sometime later, at the end of cycle 4, instruction 2 is going to graduate. At the end of cycle 5, instruction 3 is going to graduate. Okay, and so, all of these tasks are being coordinated with a clock, right? So there's a clock that spikes up at this point of time, then goes down, and then spikes up again over here. And then the same process kind of repeats. Right? So at every rising clock edge, you have instruction C or you have stage C finishing its task and graduating an instruction. And every rising clock edge, happens after a certain amount of time. If you assume that my unpipelined task, took 3 nanoseconds, it means that each stage now takes 1 nanosecond. Okay, so now, if I were to quantify this a little bit more, for my unpipelined design, since it took 3 nanoseconds to do the entire instruction, my clock would be longer as well, right? And so my clock speed is 1 by 3 nanoseconds, which is 333 megahertz. With my pipeline design, with 3 stages, my clock speed is much faster because there's a clock spike, there's a rising clock edge every 1 nanosecond. So my clock speed is now 1 gigahertz. And that's kind of what I'm doing. I'm doing pipelining to try and improve my clock speed, because now my clock is running faster, and at every rising clock edge in both my unpipelined design and at my pipeline design, I have one instruction that finishes and leaves the microprocessor, right? And the faster my clock speed, the more frequently that I'm finishing instructions. Okay, so in this discussion, I've obviously glossed over a bunch of details. I haven't talked about things like dependencies, which is stuff we'll discuss a few videos later. And I've also not talked about pipelining overheads, which is something I'll discuss in the very next video.